Hello. Today we have a second problem on energy conservation, including rotational kinetic energy. We have a metal ball with 125 grams of mass and 1.25 centimeters of radius. It rolls without slipping on the horizontal floor, and a ramp was placed on the floor, and the ball rolled up the incline or the ramp without slipping to a distance of 1.22 meters along the incline before stopping. The ramp has an angle of 17 degrees. So question 1, find the speed of the ball and its rotational kinetic energy before it reached the ramp. So how fast did it have to roll in order to get onto the ramp and stop to a certain distance? And then question 2, how far along the ramp did the ball roll when its speed was reduced to half its speed on the floor? So I have diagrams here. This is 1, timestamp 1. So the ball is rolling. So it's rotating and translating at the same time. And this is 2. The ball is still rolling, but not as fast. And it's also translating, but not as fast. So this is about half the speed. And then timestamp 3, the ball is at rest. And we know the mass, right? Mass is 0.125 kilograms, and the radius of the ball is 0.0125 meters. Okay, so since we added rotational kinetic energy, the total energy now looks like this. Mechanical energy is translational and rotational, and then gravitational potential energy. So let's set up an axis that points up. So this is going to be an axis that keeps account of the gravitational potential energy. Let's call it y. So y equals 0 here, and y equals something non-zero. We don't know what it is, and now y is equal to something here. Excuse me. That's related to how far the ball has rolled up the ramp. So ball went up 1.22 meters along the ramp, and this is y is 3. So we need to use trigonometry to calculate this y is 3. Alright, so we'll do that later. And do we have y2? Here, let's do a y2 here. So y2, and using energy conservation, we can find y2, but our question was how far along the inclined plane of the ramp. So if I call this L, I can call this L2. So we'll use the same trigonometry to find out L2 after I find Y2 here. And over here there's no Y, Y is equal to 0, right? So let's write down the exact expression of the mechanical energy. So the kinetic energy of translation, 1/2 mv squared, and rotational kinetic energy, 1/2 I omega squared, and then gravitational potential energy mgy. So because we were told that the ball has this rotational inertia, this is for a solid sphere, we can replace that omega with this. We know that omega r equals v. This is only true if the ball does not slip. So anywhere you see on the question that it rolls without slipping, you can use this. So if it rolls with slipping, for example, if it rotates faster and translates, then this omega r will be greater than v. So that's like trying to start your car after you stopped it on some icy surface. Your wheels will be spinning, and you're not translating very much. And also the other way is when you're trying to stop on icy surface, when you're almost able to stop your car's wheels, your car is still translating, so the omega r is less than v. In neither situation is this equal sign going to hold. So we have to know that if there's no slipping, then we can use this. So let's calculate further. 1/2 mv squared plus 1/2 2/5 mr squared, and omega is v over r, so v squared over r squared, plus mgy. And we can simplify, divide out these, and divide out these. So we have 1/5 mv squared. That is the rotational kinetic energy. The translational is always 1/2. So if we combine 1/5 and 1/2, we have 5/10, and here's 2/10, so 7/10 mv squared plus mgy. So this is the new kinetic energy, including translation and rotation. It looks a little different. Well, it's a little larger than 5/10 for sure, because there's this rotational kinetic energy that's included. Alright, so now we have figured out the expression. We can write E1, so this is the mechanical energy at timestamp 1. So we have translation but no rotation, translation rotation but no height. So 7/10 mv1 squared plus mg0, right? And we don't really know the v1, so we just leave it. Over here, this timestamp, we have E2, which is equal to 7/10 mv2 squared plus this unknown height, so mgy2. But we do know that the speed has dropped to 1/2 its original speed before rolling up the inclined plane, so we can replace that v2 with half v1. So here v2 equals v1/2. Here's v1. So replace this with half v1. You square the half into a quarter, and that quarter the 4 goes into the denominator. You get the 40 in the denominator. 7/40 v1 squared plus mgy2. So that's as far as I can go. And now let's go to this timestamp 3. We know there's no kinetic energy, so 7/10 m0 squared, and then plus mgy3. So let's calculate y3 here. I have some space here. So y3 over this L3. So L3 is equal to the sine of 17 degrees, right? So we could use that to find y3. So y3 over sine 17 degrees is equal to L3. So y3 over L3 equals sine 17. So you can do L3 sine 17 degrees. Now you can pause the video and just plug in the number in your calculator. And I got 0.357 meters. Okay. So now that we know y3, we can calculate energy E3. So it's equal to m times 9.8 times 0.357. So this is approximately equal to 3.50 m. I'm dragging the mass m here because later you'll see that all of these terms will contain m, so you can divide out the m without having to plug it in. And for units, let's be extra careful. We put the units in parentheses so they don't confuse us with meters and mass. Okay, so now I have E1, E2, and E3. I can use my energy conservation. E1 equals E3. Because I know E3's exact value, and I equate that with something I don't know, the M1, not M1, V1. So now we have this 7/10 m v1 squared equals 3.50 m. So divide out m, I can solve the v1 squared. So v1 squared is equal to 10/7 times 3.50. 3.50 is half of 7, so that produces a 1/2. 1/2 to 10 is 5. So that's nice. v1 squared is equal to 5. So v1, if you square root 5, is approximately equal to 2.23 or 2.24, depending on how you round. Okay, so I'll put the units in. Alright, so that's how fast the ball was rolling before it encounters that inclined plane. So now let's move on to the middle section. We can find out, oh right, I forgot we should calculate this. The kinetic energy, rotational kinetic energy So the rotational kinetic energy, if we go back over here, this is that rotational kinetic energy, and it is 1/5 mv squared. So K rotational is 1/5 mv squared, and at this point in time I can plug it in because v squared is 5, that divide out 1/5, and I just have this m, which is equal to 0.125. But now units have changed into joules. Alright, so that answers the first question. And the second question is, how far along the inclined plane or the ramp did the ball roll when its speed has reduced to half its original speed? So I'll use energy conservation here. E2 equals E3. Because E3 is a known quantity, I can easily say an unknown equals known. And I can make my life a little easier. So 7/40, keeping the m. The velocity v1 squared has been calculated here. So this is times 5. Plus m times 9.8 times y2 equals 3.50 m. So divide these out, I get an 8. So this is 7/8. So divide out m, so that's a pure 7/8. So I have this 9.8 y2 equals 3.50. Here's 7/8 minus 0.875. So I can calculate y2. y2 is equal to this whole thing divided by 9.8. So with your calculator, find the value after pausing the video. Okay, so we're back. This is 0.268, and we were asked the lengths here, how far along the inclined plane. So I need to calculate that back because I have this relationship. The height and the length is related this way. So the length is equal to the height divided by the sine of the angle. So L2 is equal to y2 divided by sine 17 degrees. So pause the video again and find this value. Okay, we're back. So 0.914-ish meters. Okay, so that whole problem was solved. So excuse me. So what I did here was because this shape is a regular shape, it's a ball with this solid sphere rotational inertia, I did this. I combined the translational and rotational kinetic energy terms into this very convenient kinetic energy term. So I'm using this for the timestamp 1 and timestamp 2. So when I calculated, I only needed one term, the combined kinetic energy. And that includes both translational kinetic energy and rotational kinetic energy. So I just equated energies at different points in time, and then I solved for the initial speed. After that, I can calculate for rotational kinetic energy alone, and then I can do another energy conservation to find out how high the ball has rolled up before its velocity has basically reduced to 1/2 its original, and then I use trigonometry to find how far along the inclined plane. Thanks.